ግዛቸው ኦኬ ብዙ ሰው ጆይን እያደረገ ነው። ሌት እንጀምር ወይስ እንጠብቅ ትንሽ?
መጀመር እንችላለን።
ገና
ትንሽ
እንደዛ
ብንጠብቅ ጥሩ
ከሆነ
ነው።
እንጀምር እ
ትንሽ ብንጠብቅ ጥሩ ነው። የተበታተነ ስለሆነ
ኦኬ ሌላ ክላስ ነበረ ወይስ?
አይ ዛሬ ካላንደር ስለሚዘጋ
ሆሊዴይ ነው ቀኑና
ኦኬ
ተበታትኖ ነው አብዛኛው ክላስም ስላልተከፈተ ነው።
ኦኬ
ትንሽ አንድ 2 ደቂቃ
እሺ እሺ ኦኬ አይ ቲንክ ብንጀምር ይሻላል። አሁን ብዙም ሰው ጆይን እያደረገ አይደለም ከአሁን በኋላ። ኦኬ ይሰማችኋል በደንባል?
ይሰማል። ሰው ይሰማናል።
ኦኬ ሰው ባለፈው ሳምንት እንዳልኳችሁ ዛሬም ትንሽ ስለ ሚኒራሎጂ ነው የማወራው። አይ ዶንት ኖ ሳምሃው የተወሰነው ልታውቁት ትችላላችሁ፣ የተወሰነው ደግሞ እንደ ሪቪዥን ስለሚሆን ብዙም ችግር የለውም። ግን ስለ ሚኒራል ፕሮሰሲንግ ዝም ብሎ ዲቴል ነገር ከማውራት ይልቅ መጀመሪያ አንዳንድ ነገር አንደርስታንድ ብታደርጉ ሚኒራል ፕሮሰሲንግ ለማስተማር ስለሚቀል ብዬ ነው ይሄኛው። ሶ ጥያቄ ካላችሁ ወይ ፋሚሊየር ከሆነ እንደ ሪቪዥን ነገር ቁጠሩት። Okay, so I probably classified my lecture into a few sections today, and we'll be looking at different ores in different sections. Probably gold ores are common, or we are going after extracting gold in many places anyway. So we'll start our discussion with gold ores. So my discussion is mainly around what are the different types of gold ores that we find in nature, and what are the typical mineralogies associated with them, and what are the challenges that are often encountered with processing gold ores. So typically we classify gold ores into two main classes. You have either a refractory gold ore or a free milling gold ore. So that's typically dependent on the mineralogy associated with them. So some gold ores are easier to process and extract the gold out. And if, for example, you use a typical process involving gravity concentration and cyanide leaching, and you recover, say, greater than 90% of the gold, then essentially you have what we call free milling gold, so easy to process gold. If recovery is not quite high, for example, if the recovery you get using a standard gold cyanidation process is less than 90%, then we say it is a refractory gold ore. Of course, this 90% is not always related to its mineralogy. Maybe you are running the processing plant very poorly, and because of that, your recovery is quite low. But typically, as a measure of whether a gold ore is refractory or not, we take the standard cyanidation test and say, depending on the recovery, more than 90% recovery is free milling, slightly easier or direct to process. And anything below that is, of course, refractory. It means you would probably need longer process to be able to extract the gold out. So for the refractory ones, you could probably have subdivisions again. So you could have, say, refractory, which is mild. So in this case, if recovery is, say, between 80 and 90%, if it's moderately refractory, probably you're looking at somewhere between 50 to 80% recovery. If it's highly refractory or severely refractory, then you have less than 50% recovery of gold. So as I say, this is very broad. If you were doing the correct thing, doing processing, and you get these numbers in terms of recovery, then you can categorize gold ores into these two. So then when I say, if you did the correct thing, maybe at a plant stage, you are getting 90% recovery or 70% recovery, regardless of what type of ore you're recovering or processing. But when we try to determine whether it's a refractory or free milling, we can probably run a simple lab-based process. So for example, we say we take a sample from our head, and we say, okay, mill it to about 75 micron. In this case, 80% passing 75 micron, and put it through a cyanide solution, 0.05% cyanide solution for about 24 hours. And then now you have leached it for 24 hours. You take the residue, separate it out, and you take the filtrate and you analyze for gold. So when you started before leaching, you have a sample with a known amount of gold. After leaching, you have dissolved the gold out. So if all the gold out was dissolved out from the sample, you have, say, 100% recovery, which doesn't occur in reality. But the idea is, I know what I have started with. I now leached it, dissolved it, and depending on how much is left undissolved for gold, we can work out how much has dissolved. So the recovery is based on how much has dissolved. And therefore, for the sample to start with, you can analyze using, say, an XRF. You have a gold in the sample. And once you dissolve it with cyanide, you have a solution, which again, you can use methods like ICP, determine the amount of gold in the solution and compare the two to work out how much gold has dissolved using a standard cyanidation. Thus, once you do this simple test, you can go back and then talk about how much gold has been recovered after leaching. So then we say, okay, more than 90%, say 95% was recovered. It shows that the sample you have or the ore you have is probably straightforward to process. If you get something like 60% recovery, it's telling you that there is still some gold locked in the sample. So in this case, it could be very fine grained gold, and therefore the cyanide was unable to attack it. And so that gold still remains undissolved. And therefore, you could say that is a refractory gold ore. So you need pre-treatment methods such as roasting and oxidation before you go out there and process something like this. So that's why when we talk about processing or mineral processing of gold ores or ores in general, we need to know how easy or how difficult it is to process them. And one of the things, for example, we do for gold ores is just determine whether it's a refractory gold or a free milling gold. From what I have briefly read, I think in Ethiopia, most people treat gold ores as if they are free milling. So whether this is due to lack of detailed mineralogical assessment or not is probably something to be seen. But typically, you can't just assume the gold ore is free milling and go straight with leaching and recovery of the gold. You probably have to first study and investigate the mineralogy of the ore you have before you determine whether you just go with gravity separation followed by leaching or whether you need to do pre-treatment methods such as oxidation before you go and leach the material. So broadly speaking again, and in this case, more related to gold ores, there are a number of different types that you find in nature. So for those of you from geology, you probably have a good understanding of the different ore body and the zones that we have in a given ore body. And in this case, towards the top, of course, you have the leached zone. Just underneath the leached zone, you have the oxide zone. And there are a number of occurrences of gold in that oxide zone. So typically, that tends to be free milling, and typically that tends to be coarse grained. And therefore, you could probably just go ahead and straight put it through a gravity separator and leach it and recover the gold. Okay. As you go a bit deeper into the ore body, you have the secondary sulfide zone or the enrichment zone, followed by the primary zone. So in the secondary sulfide zone, you have a number of different sulfides hosting the gold ore. So in this case, you could have iron sulfides hosting the gold. You could have, for example, arsenopyrite, which is hosting the gold, and a number of sulfide, chalcopyrite, pyrite, and so on. So typically, if you have something like this, so this is now gold locked in sulfides. So the first thing we'll do normally is to first separate out the sulfides from the rest of the gang. So in this case, you could use flotation to separate the sulfides from the rest of the gang. And once you have the sulfide concentrate, you can go ahead and do cyanidation. And in some cases, you might need to do pre-treatment, but generally, cyanidation may work well. Okay, as you go and look into other gold ores, some gold ores are carbonaceous. It means there is a carbon material in close association with gold, okay? Or maybe the gold is finely disseminated in carbonaceous matter. And there are gold ores where you find copper with them as well. So in this case, typically chalcopyrite hosting the gold. And there are other cases, especially in Australia here, in Western Australia, we have a telluride bearing gold, which is a gold telluride. And also in some cases, we have bismuth, antimony, and so on that are in close association with the gold. I don't know what happened. Looks like many of you were just disconnected. ኦኬ ሄኖክ እና ጌታሁን ብቻ ናቸው የሚታዩኝ ጆይን ያደርጉ። ሌሎቻችሁ ዲስኮኔክት ሆናችኋል ሰምሃው። ሄኖክ ይሰማል?
ይሰማኛል ዶክተር። አይ ቲንክ ኢንተርኔት ፑር ነው እኛ ሀገር እኮ እና
ኦኬ ሁሉም አንዴ ተቋርጦ ይመስላል
ነው ይመስላል። ኦኬ
ያ ይታዩሃል። ሌሎች ጆይን ያደርጉ። እኔን የምትታዩኝ አንተና ጌታሁን ብቻ ናቸው።
የሉም ወጥተዋል። አዎ ዲስኮኔክት ሆኗል።
ኦኬ ኦኬ እሺ። ስለዚህ ጆይን ካደረጉ እንጠብቃቸው
ይሻላል። እሺ እሺ ዶክተር
እሺ። ታንክ ዩ ሄኖክ።
አይደለ 395 አዲሱ ነው 395 ያመጣችው ደስ ደስ
ሁለተኛው ያዳነን ማየት ፈልጋለሁ። አሁንም ቢሆን ማየት ፈልጋለሁ። አሁንም ነው ሆነስ
ቆይ ግን ሌላው ማለት ነው አሁን
ያዳነና የወራሽን ማየት ፈልጋለሁ። ለምን ስለገባ ምናምን አይደለም ብገባ ራሱ ማየት ፈልጋለሁ። ምን የትኛው ጋር ነው ስፔሻሊ የወራሽን
ብዙ ሰው ጆይን ለማድረግ ስትራግል ያደረገ ይመስለኛል። ምን ይሻላል? ሌላ ቀን እናድርገው ኢንተርኔት የማይገኝ ከሆነ? ኦኬ Okay, I think some of you managed to join back. So I'm assuming it's to do with the internet. So let's try one more time and see if it is sustainable. Okay, otherwise we'll probably have to, I don't know, maybe schedule another day, but let's see how it goes. Okay, so hopefully more can join as we go. But what I was trying to say here in this slide is that there are different types of ores, and we can already work out this type of ores for gold, that is, and understand the mineralogy and predict the processing challenges that are associated with each of them. Okay, so for me, it doesn't make sense to just go straight and talk about mineral processing before giving you some kind of context. So in this lecture today, what I'm trying to give you is some kind of context as to why we process certain minerals in a certain way. Okay, so we're not going to do the processing blindly. We need to have some idea of what we're dealing with, and already by looking at the mineralogy, we can predict some of the processing challenges associated with gold ores. For example, if someone brings to me a very large deposit of gold, but there is a significant amount of carbonaceous matter in it, okay, before I even talk about the processing, I can already sit down and work out some of the challenges that could be encountered during processing, okay? So that's why we need to have that thorough understanding of the mineralogy before we go ahead and process it. So what does a typical gold ore body look like? Okay, so as I was saying earlier, so the top zone there, probably have the Goshan zone at the top, and then the leached zone just underneath that. But from mineralogical point of view, what's more interesting is the one underneath the leached zone, which is also the oxide zone. So if you have a gold ore body and you hit the oxide zone, in the oxide zone, typically we find free gold or gold locked in quartz or clay or oxide material or iron oxides in this case. So already this is weathered, and it is possible for us to recover some of this gold using very simple methods, typically using gravity methods. Okay, so if someone was doing an open cut mining, for example, typically what we are looking at in the first, say, 40 meters or so is that oxide zone. And usually the gold is coarse grained, and therefore I wouldn't worry too much about how you process it, because processing shouldn't be complicated at that stage. The problem is this zone is not very thick. It's probably going to last a couple of years. After that, you have to go a bit deeper, and therefore you have to think about how the ore body changes as you go deeper and deeper. So once you exhausted the oxide zone, most likely you're going to hit that secondary zone or secondary sulfide zone. It's also called the supergene zone. And that's where you find a number of sulfides. So sulfides, which typically host the gold, in this case, if it was a pyrite, chances are you could find some other associated sulfide with it, which are called secondary sulfides because they're derived from the primary sulfide. In this case, you could have things like, for example, pyrrhotite or arsenopyrite and so on. Okay, so the sulfide zone typically contains a number of sulfides. But again, if it's a gold ore body, that is where you find the gold as well. So the vast majority of it, 90 plus, 95% plus, is going to be a waste rock. But the gold is most likely going to be confined in that sulfide region or in that sulfide mineralization. So typically for this kind of ore body or this zone, you're going to require some kind of concentration method before you go with leaching. Okay, so mineral processing then comes into play, and it's all about what do we do to separate the sulfide, which is containing our target gold. Going deeper a bit, which is now the primary or hypogean sulfide ore body zone. And in this case, you're probably going to find most likely one sulfide. It could be a pyrite hosting the gold. And the mineralogy is not that complicated. So you don't get a number of sulfides at these depths. You're more likely going to find one primary zone and one sulfide mineral, in this case, either a pyrite or say chalcopyrite. And again, in terms of grade, it's not going to be very high grade to that of the supergene zone. And gold is not going to be free and mobile, just like the oxide zone. It's going to be most likely locked within the primary sulfide itself. And typically we do underground mining to access that depth anyway. But the whole point of this slide is as you go deeper and deeper and deeper, you hit different ore bodies, different zones, and different mineralization. So you can't assume whatever you had to process the oxide zone is not going to be the same for the secondary oxide zone, the secondary sulfide zone or the supergene zone. And whatever processing circuit you had for that is not going to be able to work for the primary sulfide zone. So you have to either consider adjusting the processing plant. Okay, so you have to modify something during processing to be able to handle different zones from the ore body. Otherwise, you're going to get very poor recovery. Or other peoples or other plants, for example, consider blending everything. So instead of just mining, say, the oxide zone first, they will blend everything. They mine everything at one time, and they blend everything, and the processing plant can handle that blended material very well. So again, we need to account for what is going on and how the ore body is varying as we go in deeper and deeper. And our processing plant also needs to account for that variation in mineralogy. So if, for those of you who might have visited a mine site, okay, and maybe if they were doing an open cut mine, it's actually very clear, at least to see the different zones. And for open cut mine, you could probably work out where the oxide zone is. Usually the oxide zone is the top surface and it tends to be reddish brown. Okay, it's not very thick, but at least the color is very typical in many places. The reddish brown coloration stands out because of the decomposed rock material. Primarily, you would probably have iron oxides there. And if that's the case, then, and you have gold deposit, the gold is going to be free and easier to recover and process. So in the sulfide, so essentially what might have happened in that oxide zone is that your primary sulfide has been oxidized and the gold has been exposed because the rock has weathered. So essentially the rock has been transformed from something like a sulfide, such as pyrite, through natural oxidation. The pyrite decomposes and oxidizes into more porous material. And that's why the gold is also exposed because of that natural process. So I don't know if you can see my pictures there, but as you can see, the one on the left shows that there is some pyrite, or the pyrite hosting the gold itself. But as you can see in some of those fractures, you can clearly see some of the gold appearing in the fractures, and that's mainly because of the weathering of the pyrite, which then exposes some of the gold that was already locked in the pyrite. So obviously, to be able to observe this, you're looking at coarse-grained deposit and free gold locked within the pyrite itself. So in that oxide zone, what you're looking at is naturally the pyrite has undergone oxidation or weathering, and therefore, due to that, the gold has been exposed. So if you find gold in the sulfide zone, in the supergene enrichment, or in the primary zone, typically the gold is going to be very fine grained and disseminated all over the deposit. So it's not going to be as straightforward to process as well. And that's why I was mentioning earlier, in those cases, if you just concentrated the gold and put it through a leaching tank, it's not going to recover most of it. So again, you might get poor recovery simply because in that zone, although you still have gold, the gold is typically locked. So you have to do some sort of oxidation. So the oxide zone shows a naturally oxidized material, but for the deeper zones, you need to oxidize it yourself. And this could be, say, using a roasting method, or using a biological oxidation roast method, or using a pressure oxidation, or whatever the case may be. But it needs to undergo some kind of pre-treatment before you leach it out. So again, just a very brief introduction into the different types of primary gold ore deposits. So in Australia, most gold deposits are orogenic in type. Okay, so essentially gold hosted in greenstones and in common association with sulfides. And the gold tends to be finely disseminated in sulfide, and you would probably require a slightly more complicated processing for effective extraction of the gold. Some gold ores have copper in them. Okay, so you find both the copper and the gold in reasonable amounts. Okay, so these are typically called copper gold deposits. And if you guys have heard about porphyry copper deposits, these are very large, low-grade copper deposits, and they're found in many places in the world. So because they are very low grade and very high tonnage, usually the plants that you have in those type of deposits are also very large to be able to handle a large tonnage. But the good thing about this type of deposits is that you can recover both the gold and copper, and therefore they have very reasonable economic returns. There is another gold type, deposit type in South Africa. It's called the Witwatersrand deposit. And this type of deposit, usually still the gold is embedded in a rock sequence, but the gold is coarse grained, very roundish in shape, sort of looks like a placer deposit. And again, that deposit in South Africa used to be one of the largest sources of gold for many years. Some gold deposits have silver in them, actually very significant amount of silver in them, and they're referred to as epithermal deposits. Again, in those type of deposits, we're recovering both the gold and the silver as the byproduct because they contain substantial amount of silver in them. Disseminated types are, as the name implies, the gold is disseminated all over the rock, and in this case, it's fine-grained, and processing is slightly more complicated. So you might consider fine grinding and so on to be able to extract the gold. Another challenge associated with these ones is hosted in carbon. So the carbon material is a host, and it actually makes gold processing very challenging, because in typical cyanidation process, for example, you dissolve the gold, and as soon as you dissolve the gold in leach tank, the carbon absorbs the gold onto its surface. And because this is a very fine carbon, you end up losing the carbon and the gold together, and therefore it complicates the whole process. So something like this, disseminated gold deposit with carbon in them, that we call them sometimes double refractory, because one, gold is fine grained, so it's refractory, and two, it contains carbon, and carbon is also very challenging to deal with during processing. So these things can already be worked out through detailed mineralogical investigation. Okay, so how about in the Ethiopian context? Of course, you are probably aware that there are a number of potential occurrence of gold in many parts in the country. So the western part and the northern part is well recognized, and there are also some gold deposits in the southern parts. But from the readings I've done, it looks like most of the gold actually occurs in orogenic type gold deposits, where the gold is actually hosted in sulfides. So in this case, for example, primary mineralogy for this type of ore bodies is pyrite hosting the gold. So again, depending on what you look at, gold can be coarse grained in pyrite, which essentially makes it easier to process, or the gold can be microscopic. So very finely disseminated gold all over the sulfide mineral, which now means that you have to first separate out the sulfide, in this case a pyrite, and then have to do some kind of pretreatment before leaching it directly. Okay, but I think from also the review of the plants I have seen, most of the plants or the circuits are very simple, which I believe probably results in some of the losses in gold, and they probably are getting very poor recoveries for gold. So when I say poor recovery, typically a good recovery for gold is more than 90%. So you essentially recover 90% or more of whatever head material you started with. That is a reasonable recovery for gold. If it's less than that, your recovery is very poor, and therefore your method for processing is actually not appropriate. Okay, so again, in Ethiopian context, that probably may not be what is happening in reality. I think from the review I've done, I think some of them operate at less than 70%, which actually shows a very poor performance of gold recovery. So why do we get poor recoveries? It's mainly because we're not understanding the mineralogy properly. So in this case, we need to first locate where the gold is distributed. And depending on where it's distributed, whether it's coarse grain or fine grain should be determined. And if it's fine grained, we need to sufficiently liberate it first before we actually talk about leaching or extraction. So if that understanding is missing, if we don't have a very good understanding of the mineralogy, so we're most likely blindly processing it, and therefore we're just hoping to recover the gold. But again, we get poor recovery simply because of our lack of understanding of mineralogy. So that can be a problem. And obviously understanding the mineralogy of the ore takes many years of studies, and it's expensive to do as well. So maybe not everyone is committed to understanding that. So I've talked about some of that understanding required last week as well. So typically, visible gold is easy to identify and therefore easy to process. Invisible gold, or what we call the submicron gold, is the one that is more challenging to characterize to start with. And once you characterize it, once you locate where the gold is, then you can probably talk about slightly more complicated ways of processing them. But currently, there is technology that helps us identify and characterize the mineralogy, and therefore that should be utilized in cases where there is the opportunity. So this, for example, can include simple microscopy, where you can see visible gold or microscopic gold, obviously straightforward for processing, but in cases where coarse-grained gold is not visible, where the gold is finely disseminated in the rock, you will need to do something more detailed using electron microscopy and so on. Okay, so again, I mentioned cyanidation a couple of times already. That's at the moment anyway. That is the typical method for processing gold concentrates, because we know sodium cyanide dissolves the gold really well, but for that to work, you need oxygen. And therefore, now you have a big leach tank with cyanide in it. You add your material, you agitate for a few days typically. So if you just have cyanide and the ore, it doesn't actually dissolve well. So you need to inject certain amount of oxygen, dissolved oxygen, into the leach tank to be able to aid the dissolution rate. This is something you should learn in your hydrometallurgy class. So I'll probably don't go too detail into this one. So what I wanted to mention for my case here for this course is typically in cyanidation, there are two issues. One, cyanide is consumed a lot. So in this case, for example, for every 4 moles of gold, you need 8 moles of cyanide, and you need oxygen. So why is that a problem? It's a problem particularly where you have minerals that react with the cyanide. What we want is the gold to react with the cyanide, but some minerals actually react with the cyanide, which means it's consuming your cyanide before it reacts with the gold. And some minerals are easily oxidizable, which means instead of helping the cyanidation process, the oxygen is being consumed by another mineral. Again, that is going to affect the possibility of dissolving the gold effectively. So these are actually some of the challenges we need to be thinking about when we do characterization of the ore itself. So these type of minerals are called either the cyaniders or oxygen consumers. So what are the cyaniders? Are simply cyanide consumers. So what are they? Especially when you have copper and gold together, the copper minerals actually consume a lot of cyanide because they're easily soluble in cyanide. So in this case, instead of dissolving the gold, the cyanide reacts with the copper minerals, and therefore your gold leaching rate will drop significantly. If you have something like pyrrhotite doesn't have any value, so it's just a sulfide, an iron sulfide. We don't get any value from it. But if you have pyrrhotite in the ore, it's going to react with oxygen. It's going to consume the oxygen that you were trying to use for cyanide leaching. Again, that is going to inhibit the gold dissolution with cyanide and a number of other oxygen consumers and cyanide consumers. So again, our mineralogy work, before we talk about leaching and extraction on all that, which is nice, but we need to first deal with what we have in the ore. So in this case, for example, if you have too many copper minerals in the ore, actually leaching with cyanide is not the best solution. So I'm not going to worry too much about leaching in this case, because I know the copper minerals are going to consume my cyanide, so cyanide leaching of gold is not going to be effective. What do? I probably would first concentrate and then smelt rather than leach. So again, in this case, the mineralogy is dictating what processing route I'm going to take. So as I said here, typically when there's copper minerals that are abundant in the ore, and I have gold in the ore as well, instead of using cyanide, I would rather use smelting, which can deal with both the copper and gold in the ore body itself. So in this case, you smelt, you recover the copper, and from the residue, you can collect the gold as well, and happy days. So that should be a lot more economic to run with, rather than just because you say cyanide works for gold, it doesn't mean it works for all gold ores, okay? And as I said earlier, if the material has carbon in it, again, cyanidation is not going to be effective. So that's why we need to first understand the mineralogy before we talk about further processing of the ore itself. Okay, so this micrograph here shows, a typical photo micrograph that you can conduct to be able to locate where the different minerals are. So some of them are hosting gold. In this case, the gold is hosted in pyrite, but also with that, you have the cyanide consumers I've talked about earlier, such as the chalcocite, native copper, and so on. Chalcopyrite is usually not a problem if it's the only phase, although it's a copper mineral. Chalcopyrite doesn't dissolve that well in cyanide, so you might get away with it. But if there's an abundance of chalcocite, native copper, and so on, those are going to be a problem during cyanidation. Okay, so if I have refractory gold ore, what are the things that I will do? The first thing you should be looking at is to concentrate the sulfides. And typically for that, we use flotation. Okay, so that typically will give you maybe 5% of the stream that's coming to the mill. So the 90-something% will be completely rejected before you even look at cyanide. So in this case, we say, okay, we know gold is hosted in the sulfides. Maybe it's finely disseminated gold in the sulfide, but regardless, typically, instead of, for example, considering gravity separation only, you probably would be better off if you looked at flotation first. Now you have the concentrate after flotation. You can take that concentrate, you can do all sorts of treatment with it. So you can do roasting, as I said earlier, which is becoming a bit of an older technology now. It works well, but it generates sulfur dioxide, which is not environmentally friendly. So these days, I think it's, especially in Western countries, it's becoming a problem to get the license to be able to run roasters in a plant. So instead of roasting, maybe you can consider more environmentally friendly treatment methods like pressure oxidation or fine milling or biological oxidation. Once you oxidize this concentrate, then you can put it through a leach tank and it should work well. So doing this will give you a high recovery. So maybe someone has this, but they're not doing any pre-treatment. They just produce the concentrate and put it through a leaching tank. They're going to get very poor recovery already because they're not understanding the mineralogy of the ore. And therefore, as a result of that, they're not putting any treatment before cyanidation or before leaching. And as a result of that, they're going to get poor recovery. So these things can already be determined if you had a good understanding of mineralogy. And that's why I was keen to do this lecture before I talk about further processing. Okay, simply because if you know what's going on, you probably understand why you're doing a typical processing circuit or a typical processing method for a given ore. Okay, I think there were a couple of disruptions. Maybe I'll just pause a little bit and see if anyone has a question so far. Okay, is it a very familiar topic? Or is it helpful?
Sure, it is helpful, Doctor.
Okay, Henok, ምን አልከኝ? አልሰማሁም በደንብ።
Yeah, it's helpful actually.
Okay, yeah,
Yeah,
very
it's
good.
new concept. Yeah.
Okay, very good. Okay, so again, what I thought I will do is that was a brief for gold ores. I will do the same for base metal deposits, and also I will do the same for ferrous metal deposits. So that next time we talk about their processing, we understand where we're coming from. So we're not just blindly trying to process them, but we know why we're trying to process them a certain way. So again, I can go into details about each of these topics, but for this course, it's not relevant to go into details. I just want to give you some of the basic information so that you are up to date, okay? Or at least you have a brief understanding of why we're doing things a certain way. So when we say base metals, typically we're talking about copper, lead, and zinc. Okay, so when we say base metal deposits, then we're just talking about deposits of copper, lead, and zinc. When you find these deposits, usually they're going to be very high volume, but they're very low grade. So I hope you know the differences between volume and grade. So volume is just the tonnage. So how much deposit is available, okay, in a typical area. Grade is how much copper is in that deposit, or how much lead is in that deposit, or how much zinc is in that deposit. Maybe we're talking about percentages here. So it could be 0.5% or 5% copper. Okay, so grade tells you how much of that specific commodity or element. Volume is more tonnage, how large is the deposit itself. So what are base metals? As I said, the copper, lead, and zinc. So they're not precious metals. So gold, silver, platinum, palladium, and so on are precious metals. And they're not ferrous metals. Ferrous metals are something like iron, manganese, chromium, titanium, and so on. Okay, so they're neither of those. And therefore, because of those different properties, they also occur slightly differently from, say, ferrous metals or from precious metal deposits. And usually when you find a copper deposit, you will tend to find lead with it, and you tend to find zinc with it as well. Okay, so in this case, maybe when you look at the typical deposit, you might be looking at someone extracting copper and zinc at the same time, because usually they occur together. Or maybe a plant that encounter maybe extracting copper, lead, and zinc at the same time in one plant, because they tend to occur naturally in close association. When we look at a typical base metal deposit, most likely you are going to be looking at a couple of them processed and extracted, okay, from that particular mining site. And when you take a closer look at these deposits, they are actually precipitated or formed from hydrothermal processes. And that actually gives rise to very specific mineralogy, which needs to be taken into consideration during processing. So I'll talk about those occurrences in a little bit later on. So in terms of mineralogy, the main base metal minerals are sphalerite for zinc, galena for lead, and chalcopyrite for copper. Of course, you can have other secondary sulfides, such as chalcocite and so on, but the primary mineral for copper is chalcopyrite. And together with this, we also tend to find the pyrite, the pyrrhotite, and magnetite. And although these are major minerals associated with base metals, you can't actually extract any value from them. So in this case, the pyrite is going to be gangue if it occurs with base metals, so you have to get rid of it. If you have pyrrhotite, pyrrhotite is going to be the gangue. Although it's an iron sulfide, we don't really extract iron from it, okay? And essentially, with base metals, it's going to be a gangue mineral as well, okay? But they are going to be major occurrences in association with the three main minerals, which are sphalerite, galena, and chalcopyrite. So again, you could have other minor elements, secondary sulfides, including tetrahedrite, which is in some places very rich in silver and could be source for silver, stannite for tin, arsenopyrite, mainly gangue, and also you could have precious metal like gold as well. So that's why I say earlier, you could have places where you have a copper and gold deposit where you can extract both the copper and gold together as well. And the secondary sulfides or the supergene zone of this type of deposits may contain a number of secondary sulfides, including chalcocite and bonite and so on. And upper level, the oxide zone, is dominated with malachite, azurite, and a number of other carbonates, including zinc and lead carbonate. So again, just like I told you for the gold deposit, where I said, for example, in the oxide zone, primarily the gold is free milling gold or free gold. For base metal deposits, the oxide zone is usually dominated by carbonates. But these carbonates, again, can be very high in copper concentration, for example. In some deposits, you could have 20% copper in that zone, which is really high. And in the first couple of years, it might actually give you a high cash flow for the plant. But again, that's not going to be sustainable over the long term. Okay, it's going to deplete very quickly. So as you go deeper, we're going to exhaust the carbonate or the oxide zone very quickly. And again, your mining is going to be mainly based on the hypogeum or the primary zone, where, for example, if it was a copper deposit, you're going to mainly be mining chalcopyrite for, say, 20 years or so. Okay, so again, there will be considerable changes in mineralogy as you go from top to bottom. Okay, maybe the guys from geology are all over this. Maybe you are very familiar with it. Okay, maybe you're just aware, but in terms of classification, at least based on the way they are formed, you could have a number of base metal deposits. So for example, you could have volcanic hosted massive sulfides, or they're called VMS, sediment hosted exhalative deposits. These are called SEDEX for short. And typically, if you have SEDEX, you have lead and zinc, okay, with some silver in them. The VMS typically could have the copper, the zinc, and the lead all together. Some are hosted in carbonates, for example, in US, and some have undergone metamorphosis, so they are actually coarse-grained. For example, if you go to a place called Broken Hill in Australia, you actually find very coarse-grained base metal deposits as well. Porphyries are very large copper deposits, potentially with some gold in them. So there are a number of examples. So why am I talking about these ones? It's simply to give you some idea about mineralogy based on the genesis. And I'll talk about those examples here. For example, for VMS, again, if you're familiar with the topic, you know that VMS deposits are derived from black smokers. And what are black smokers? I think I have a picture showing you. So black smokers actually are processes that happen under the sea, and they actually happen to this date. It's not something that happened millions of years ago. It happened millions of years ago, but it's still happening today. And this is a process happening under the sea. So what is that process? So during undersea volcanic activities, when, for example, there's a volcanic eruption under the sea, if you go to those lines at the bottom of that slide, the hot hypothermal fluids, these contain copper, zinc, lead, and so on, will progress through the fractures and are brought about to the surface of the sea. When they come to the surface of the sea, now it is hot, so the whole area around that is hot, and therefore you're essentially looking at a hot hydrothermal fluid coming up to the surface. But as soon as it hits the surface is obviously sea, it's the seawater. There's a lot of sulfate in seawater. So the copper ion now reacts with the sulfate, it forms copper sulfide. The lead ion reacts with sulfate, forms lead sulfide. Zinc reacts with sulfate, forms zinc sulfide. So what you saw in that picture there, that dark smoke, is actually the hot fluid containing copper, for example, reacting with the sulfate, forming very fine copper sulfide dust. And the same is true for the lead and the zinc as well. So what happens is, over time, the formation of the sulfide, so the lead sulfide in this case, for example, progresses. So it accumulates under the sea and it produces debris or chimneys of very fine sulfides. So if this was to happen over millions of years, So you would actually have a proper deposit of very fine sulfide accumulating under the sea. Okay, so obviously this process happened many, many years ago. So what you find as a land now might have been the sea retreating, and therefore now it's exposing those deposits that were actually produced millions of years ago. And therefore, when people now mine VMS deposits, most likely those VMS deposits were formed millions of years ago because of this process. So the end result is that you have a debris of fine sulfides accumulating in seashores containing very fine sulfides. And therefore, when you look at VMS deposits, the texture is actually very complicated. And the sulfides are very intimately associated with one another, simply because they were derived from very fine dust of sulfide. And in this case, a fine sulfide dust of lead, zinc, and copper were all accumulating at the same time. And that's why this photomicrography shows you, for example, fine grain texture of two minerals. I think galena and pyrite are shown here. So the darker gray is sphalerite. I don't know where my writing went, but that's sphalerite. And the darkest one is most likely a silicate material. But the point is here that because of the way the ore deposit formed, it actually resulted in to a very fine grain sizes of those sulfides. What does this mean? It means that when you now mine VMS deposits, chances are the sulfides are very intimately associated. So although you have copper there, zinc there, lead there, all in one, you probably have to first liberate them from one another. And the way you do that is by just doing fine grinding. So that's why processing becomes a lot more challenging when it comes to VMS deposits. Okay, so again, for me to teach you about processing VMS deposits, for example, using flotation, I have to first tell you how they formed, what the mineralogy looks like, and therefore once you have an idea of the mineralogy, then you can see why we employ a specific processing method to be able to extract the valuables from them. Okay. In terms of locations in Ethiopia, I think there are several examples, but typically they are found in the Arabian-Nubian Shield, somewhere around the Red Sea. And there are a number of examples in northern parts of Ethiopia and in Eritrea. So there are a lot of VMS deposits around there. And I think you guys might be familiar with the Harvest project in northern Ethiopia, which has been going on for a few years before it was interrupted. But in any case, I think that is considered as one typical example of VMS deposits where typically you should be able to find copper, lead, zinc sulfides with some amount of gold and silver in them. Okay, so again, when you look at the VMS deposits and you have done a thorough mineralogical work on them, you should probably find that these are fine disseminations requiring slightly more complicated processing. But I looked at what they did for processing this type of deposit, and all they did was crush it, heap leach it with cyanide, and I think the idea there is to dissolve the gold and the silver. And then once the gold and silver was deposited, they used a Merrill-Crowe process where you just essentially precipitate it with zinc, and then you smelt and recover the gold from it, which I thought was very odd because typically when you look at a VMS deposit with very complex mineralogy, potentially fine sulfides in intimate association with one another, the easiest thing to do would be to first bulk float all the sulfides. Okay, so you mine, you float all the sulfides first, and then instead of leaching the whole material, which I think is what's happening from what I read in the flow sheet, you could probably just first separate out the sulfides, which are going to host the gold and the silver, and get rid of the majority of the gangue beforehand. And then once you have the sulfide, you could even consider straight smelting for gold and silver, okay, which could have been a lot more straightforward. And if you did that way, you probably would get a higher recovery. But from looking at just this processing flow sheet, it seems to me that this is going to give you very poor recovery unless you're just doing processing for the top part, the oxide zone or something like that, where you have a free milling gold. I think for the primary ore deposit, this processing may not be. I wouldn't personally pick a processing route like this one. So again, I haven't tried processing it. I haven't run any lab work to process it, but by just looking at the mineralogy, I don't have to even do complicated experimentation. I could probably just tell and try to come up with the best processing method. And in this case, probably maybe putting a flotation before leaching would be the best outcome to recover most of the gold out. And I looked at some of the things, and I think the recovery was less than 70% from what they were saying anyway. And that's to be expected, because in this case, gold is most likely finely disseminated in the sulfides and is probably fine-grained and not sufficiently liberated. So when you put it through heap leach, the cyanide is not going to access most of the gold, and therefore your recovery would be naturally very low. Okay. But we'll talk about details of processing later on. But in this lectures today, all I'm trying to do is associate mineralogy with consequences in processing and challenges in processing. So that could be one key consideration to be looked at. Okay, for SEDEX deposits, again, these are happening to this day. I think there are some evidence of that happening in the Red Sea again. So instead of very fine sulfides accumulating under the sea, what you have in SEDEX deposit is pretty much fine sulfide mud. Okay, and this mud can accumulate over many years, but the difference between this and the VMS is the SEDEX are layer by layer by layer kind of deposits, while the VMS deposits are simply fine disseminations of sulfides accumulating over a long time. So SEDEX has, I don't know if you can see my pictures here, but at least you should be able to see some sort of bedding of the rock sequence. So there will be some lines of dark, some lines of brown, some like which appear to be a bit grayish or lighter, and so on. But you can clearly see different bands. Okay, so these are bands of oxides and bands of silicate material and bands of sulfides, which have accumulated over many years. So these are sedimentary in nature compared to the VMS deposits. Again, what are the challenges then? Because of the way they form, if it undergone metamorphosis, it tends to be coarser-grained and easy to process. I think that sequence there at the bottom is an example. But if it hasn't undergone any metamorphosis, it still remains very fine-grained, which means liberation becomes a lot more challenging. And when you try to liberate by doing fine grinding, obviously comminution charges will be high, and also processing fine particles is very challenging as well. But at least because of the way they are formed during orogenesis, that gives rise to complex mineralogy, and therefore eventually you would need to deal with more sophisticated processing to be able to extract the base metals from them. So what are the common issues in processing for base metals? The zoning of the ore body is one challenge. And as I say, you have a number of sulfides together, so separating them from one another is very challenging. And in some places you have precious metals in it as well. Separating the precious metal out from the rest is also challenging. And in some places you have toxic elements as well. And therefore that also presents a challenge. I think I have some of these examples in the next slide, so I'll quickly go through these ones. So what do we mean by ore body zoning as one of the challenges for VMS deposits, for example? So when you look at the deposit itself, because of the way it's formed, you have what we call different zones in the deposit. So the copper is usually found at the bottom of the deposit, and this is to do with the least solubility of copper sulfides. Somewhere in the intermediate region, you have zinc-rich zone, and towards the top, you have what we call lead-rich zone. So those, again, are zoned like that because we know copper sulfides are less soluble, so they tend to be to the bottom. Zinc are a little bit more soluble, but lead sulfides are more soluble, so that's why they are presented to the top of that deposit. So already, when you look at the deposit, you have different zones. Some zones are rich in lead, some zones are rich in zinc, and some zones are rich in copper. So why do we care? We care because if the idea of your plant was to separate copper sulfide, zinc sulfide, and lead sulfide all together, but when you mine, you just pick the top zone, which is in this case only the lead-rich zone, then your plant all of a sudden has to run only for recovering the lead, and you don't have zinc or copper coming through the plant. As you go deeper, now you have the zinc and no lead and copper. As you go deeper, you have only copper. So why don't we then individually process them? Why don't we first process the lead and then the zinc and then the copper? Because adjusting for those variation and changing our processing plant as a result of that is a lot more challenging. So what we do is we first want to have a plant that can handle all the variability in the deposit. Okay, so that's why you need to come up with a strategy to blend everything so that once you put it through the plant, you can recover the copper, the zinc, and the lead all separately. So you produce the copper as a concentrate, lead as a concentrate, and zinc as a concentrate as well. So that's one of the issues related with, for example, processing VMS deposits. Okay, and therefore that variation in mineralogy actually presents a challenge for processing. Okay, so the other challenge is now you have a lot of sulfides together. So you have primarily sphalerite, galena, and chalcopyrite, let's say. But as I said, with those, you could most likely have pyrite, you could have pyrrhotite, and so on as well. In processing, these minerals actually behave very similarly. So if you put this all in a flotation cell, they all float very happily. Of course, what we want is a separate stream of galena, a separate stream of chalcopyrite, a separate stream of sphalerite. If we can't produce them effectively, what we're trying to do is, or what we get is typically we lose some zinc in other streams, or we lose some copper, we miss some copper in other streams, and so on. So we don't actually get good quality sphalerite concentrate or good quality galena concentrate or good quality chalcopyrite concentrate. Why? Because separating them from one another is difficult as they have very similar properties in, for example, flotation. So what can we do? We can maybe first try to float all of them together. So in this case, we float all the sulfides and reject the silicate material away first. Okay, maybe now we have 10% account for the sulfides, the remaining 90% is waste silicate. So that's the first stage you can do. Then you have to then look at the second stage where you have to separate the sulfides from one another. So in this case, maybe you first float the zinc sulfide, you have a zinc concentrate, you come back and float the copper, and then you come back and float the lead. Okay, but the typical strategy we use is we know lead and copper are easy to float. So first we can float them and we can depress the zinc. Okay, so depending on which one is more abundant, which one is more valuable, we can probably think about what to do in separating one sulfide from another sulfide. But because, as I said, they have very comparable properties, it's a lot more challenging. So you're not going to get 90% recovery for each of those sulfides. And therefore, that can be, again, problematic, okay, when it comes to, say, making profit during processing. Okay, so again, in addition to being able to separate different sulfides from one another, the other challenge is obviously, as I said, some of these sulfides tend to be very fine-grained, and therefore that accounts for complicated comminution, and also fine particles are difficult to process as well. Okay, so in addition to zonation, just dealing with a lot of sulfides all together in one ore can be very challenging, and this is common in many base metal deposits. And I also mentioned deleterious elements. So what are deleterious elements? These are actually toxic elements that are found in those deposits. And typically, in many base metal deposits, you have arsenic in arsenopyrite, for example. You have antimony, bismuth, mercury, cadmium, and so on. So what is the challenge? The challenge is you can't say, I have recovered my copper or zinc. I can throw away everything else, especially if you have toxic elements. You have to actually capture them and remove them safely. Okay, so this is an environmental challenge. And to capture these toxic elements, you need to add additional processing. Okay, so you need to add additional processing method to remove these toxic elements. So what is the consequence of this? It's called oxygen breathing. So costing millions of dollars actually with this kind of toxic elements. So your mineralogical assessment should also tell you that yes, you can recover the valuable, but your processing should also involve removing the toxic ones as well. So you have to deal with those potential values and toxic involved in the process. Again, it comes down to that in this problem of the mineralogy. And specific to, for example, copper ores, one of the challenges in copper ores is actually the complex mineralogy associated with it. So as I told you earlier, so in a given deposit, you have the oxide zone, secondary sulfide zone, you have the primary sulfide zone, and all these actually show different complexities in terms of mineralogy, and some are high grade, some are low grade, and therefore dealing with those issues can actually be a challenge, and therefore you need to first understand that before you proceed with. So, for example, when I say complex mineralogy, in a typical copper deposit, you could have copper, you could have sulfides, oxides, you could have carbon. So when you have a lot of minerals containing copper all in one deposit, it's actually a nightmare situation because you can't have a good processing flow sheet to be able to deal with all these minerals all at the same time. So whatever I can have for processing sulfides cannot be the same for processing oxides and so on. So I need to think about how to handle all these varieties of different copper mineralization to deal with and account for effective processing. And one of the challenges in copper is actually the presence of various oxides. So, for example, if you say, okay, my primary mineral is chalcopyrite, so I need to first handle the sulfides. So my processing should be able to deal with the sulfides, but I have oxides. There are things that we can do. For example, we can modify the surface of the oxides in a process called sulfidation, and we have to modify them to look like a sulfide, and we can process them with sulfides. Just like you do for chalcopyrite, you can probably modify copperite surface, for example, and process it the same. But to be able to think about modifying those, you need to know first whether they exist. So you need to know whether have oxides first. And once you know you have oxides, you need to know how much oxides, and then you can think about what.
Sorry, doctor, your sound is not hearable. We can't hear you clearly.
Okay, thanks. I don't know what's going on. My mind, I'm thinking it's supposed to do with internet, like it's poor connection. And it looks like it's happening for most of you guys. Yeah, so I think many of you are encountering the same problem. You got the same step. It looks like a connection problem rather than.
It shows a little bit improvement, but still there is a problem. But, we can continue.
Yeah.
Is it better now?
Yes, it's clear now.
Okay, yeah, very good. So if you missed what I was saying here, so I was just saying, especially for copper minerals, it's possible to find a lot of different types of minerals in the deposit for copper. So in this case, native copper, sulfide copper, oxide copper, carbonate copper, all in the same deposit. So our processing plant, actually one processing plant can't handle all of them, because whatever we do for sulfide copper works well for sulfide copper, but may not work well for oxide or carbonate copper. So our mineralogist should tell us what we need to be doing, at least know how much sulfides we have, how much oxides we have, how much carbonates we have. And based on those, we might need to adjust our processing flow sheet to account for that variation and the complexity of the deposit itself. But there are strategies to deal with this variation of copper mineralization, although you need to be first be aware of to be able to deal with them. Okay. Okay, any questions so far? Because I was maybe interrupted for a bit because of the sound. I don't know if you guys have just looked at the slides but have no idea what I talked about. Just let me know and can probably answer your questions. Okay, if no questions, I'll probably just proceed. So I briefly went through different types of gold deposits and some issues with mineralogy and processing. Again, briefly looked at some base metal deposits, the mineralogy, and some issues with processing. We'll do the same for ferrous metals. Okay. So typically when we say ferrous metals, we tend to focus on iron, titanium, and vanadium because they commonly occur together. But you could have other ferrous metals. So in this case, it could be chromium, could be manganese, it could be all sorts of other ferrous metals that we're interested in that are useful in everyday life. And therefore, they might be useful commodities to go after them and extract them. So again, what are the common minerals? If it's iron that we are interested in, magnetite, hematite, and goethite are the main minerals that we have to look for. There's a lot of iron in sulfides, such as pyrite and pyrrhotite, but the current technology we have doesn't actually allow us to recover iron from sulfide. Okay, although pyrite has a lot of iron, we can't actually recover it in the current technology. So when we say iron ore or iron deposits, we're typically talking about the oxides. So in this case, magnetite, hematite, and goethite. For titanium, we have ilmenite and rutile. For chromium, we have chromite. Okay, for example, molybdenum, we have molybdenite, and so on. So there are a number of deposits that we can use as sources for ferrous metals. But again, because I want to be brief, I just want you to get the main ideas. I will just focus mainly on these three deposits here. So iron, titanium, vanadium typically occur together, and maybe you can consider them together as well. And there are different types of these ferrous metal deposits. You could have magmatic deposits, you could have sedimentary deposits, and even some beach sand deposits, which are very well known and are sources for titanium and zircon and so on. So the magmatic deposits, as the name implies, they're actually derived from molten magmas by precipitation. And in this case, when you have magmatic activities or volcanic eruption, so in this case, you have a molten silica with heavy elements like iron and titanium and vanadium. So it's switching my mics on and off. I think that's what's happening. So with magmatic deposits, as I was saying, these are actually derived or deposited from molten magmas because they are denser, they settle to the bottom. And of course, depending on how fast or how or slow the magma cools down, you could have what we call massive deposits or disseminated deposits. And I'm not going to talk details about massive and disseminated, but the way they form may give rise to different mineralogies, and therefore that the way they form can actually have consequences on how we process them. Okay, so that's what I'm trying to say here. For example, if you go to South Africa, they have a place called Bushveld. In Bushveld, you have very rich chromium deposits and magnetite deposits. And in this case, we know it's magmatic deposit because of the way the deposit has formed over time. Okay, and it's common to find very thick layers of chromite or very thick layer of magnetite in those deposits. And for example, if you look at Bushveld in South Africa, they mine both the iron ore and the chromite ore. And the iron ore typically in magnetite is very rich in titanium and vanadium as well. Okay. And how do those deposits form? As I was saying, so you have a volcanic activity where everything has melted, turned it into liquid, but as it settles down, those red deposits, red dots that you see there, are actually individual crystals of magnetite or individual crystals of heavy element sinking to the bottom and solidify. Obviously, over time, that accumulates and accumulates and accumulates, and therefore you have, say, a layer of magnetite, in this case, in Bushveld, which then will be typically a very high percentage iron, which you can then go about and recover the iron from. Okay. Sedimentary iron ores are, again, as the name implies, and sometimes we call them banded iron formations. And typically, these again are either magnetite or hematite based. If you go to the US, they typically mine the magnetite based ore, and that's about 40% iron. Okay, there's still a lot of silica and silicate material in it. So the processing involved for that is to first get rid of the silica material. So you could use, for example, magnetic separation because the magnetite is magnetic, or you could use gravity separation because the silica is lighter, so you can get rid of it. Okay, and therefore once you do that, you can then take the iron concentrate and smelt and produce steel. In Australia, we have banded iron formations, but this iron deposit has undergone a number of years of metamorphosis, and therefore it has actually transformed from magnetite to hematite. And in that process, it actually gives rise to very high percentages of iron in deposits, for example, 60 to 65% iron. So what we find in Australia in a place called Pilbara, for example, is very high iron oxide deposit. So when I say high, it's typically they find about 65% iron in it. And all we do is we don't do any processing at all. So it's very high grade already, no significant amount of silica in it. So people just dig it up, crush it, and do some size management and screening work, and typically ship it straight to China and so on for making steel. So again, depending on the nature of the ore, not all iron ore is processed the same way because they have the same iron ore name, but they have different mineralogy. Some have silica material, some don't. And therefore, because of that, we can process them differently. And therefore, your processing flow sheet may differ from place to place. So what is the difference between an upgraded banded iron formation and the one that has been upgraded? As I was saying, maybe typically a magnetite should be maybe about 40% iron, or between 36 and 40% iron. And it looks like the one shown in that picture there, where you have a chert or a silica material banded with iron oxide. Okay, so that picture that shows the one in red shows the iron and the one in white shows the silica. And over time, this may have undergone weathering. We're not actually completely sure, but might be a weathering process which kicks out the silica. And essentially you have very high quality hematite ore. And typically that may be about 65% iron. And now when you mine this, you basically dig it up and do little processing and ship it. And if you looked at a banded iron formation, you can see this ore here, or this specimen, showing you layers of silica and layers of iron oxide. So the dark one is the iron oxide, and the reddish brown one is the silica chert, all in one. So this is obviously before metamorphosis or before weathering, but after weathering, this has all been transformed and converted into hematite. And this is one of the bigger mines around the Pilbara. It's called the Whaleback Iron Ore Mine, and just shows you the bedded iron formations. And it's a very high tonnage. You probably dig it for years and years and years, and still are left with a lot of deposit remaining to be extracted. And iron ore is one of the biggest export of mineral for Australia. And as I said, because it has already been upgraded, you typically require very little processing. Okay, so beach sand deposits, maybe you are again familiar with this, but these are essentially heavy mineral sands. And again, they are common in seashores, and they happen to the present day. You can actually see heavy mineral sands accumulating by the action of the wave in seashores. Okay, so it's commonly observable here in Australia or some other countries where there is a coastal activity happening. So what do we find in beach sand deposits? Typically we have rutile for titanium, ilmenite, again another source for titanium, zircon, even rare earth minerals containing monazite. So in monazite we have, for example, cerium and so on, which are used in batteries and so on. You can have xenotime, for example, again another source for yttrium, and a number of other commodities, even diamonds and cassiterite. So again, these deposits have undergone several years of weathering, and that weathering has resulted in the accumulation of these heavy minerals. So the accumulation of ilmenite, rutile, zircon, and so on in seashores. Usually these heavy minerals are found together with silica or quartz. So again, you have silica and heavy mineral sands. The difference in gravity is significant between them. So the silica is light and the heavy minerals are heavy. So the first thing we do is just use a gravity separator and concentrate all the heavy minerals together and get rid of the excess quartz or the excess silica. So once you have the excess silica removed, now you have, say, ilmenite, zircon, and let's say rutile. We know ilmenite is magnetic, and we know rutile, for example, conducts electricity, or it's electrostatically conductive, and zircon is not magnetic and is not conductive. So you could actually use magnetic separation to separate out the ilmenite first, and then come back, use electrostatic separation to remove the rutile, and then you have a zircon at the third concentrate. And all of this can be shipped, can be sold individually. Okay, and therefore you can have different sources of income from those different concentrates that you're producing. Okay, so here is just a photo showing you accumulation of heavy mineral sands happening even to the present day. So the ones shown in dark are actually the accumulation of heavy minerals in the seashores. Okay, I don't know if you see it very clearly, but this is a picture taken from Western Australia, and I think I have another one here where you can clearly see a very thick layer of heavy minerals accumulating in the seashores, and the white stuff there is actually sand, which is silica. So as I say, the dark one is heavy, the light one is silica, which is light, and therefore we can separate out the silica using a gravity separation first. Okay, so that's your mineral processing flow sheet, if you like. Okay, so again, very briefly going through nickel deposits. I'm not sure if we have many in Ethiopia for nickel deposits, but typically nickel deposits are classified into two. So either you have nickel sulfide or nickel laterites. Okay, so they're all abundant in many places in the world. For example, nickel sulfides are found in Canada, Russia, China, Australia, a number of places. And laterite nickel is found in many places around the world. Okay, so if you look at that table, it actually shows you some examples of nickel sulfides in the world. Okay, so example, Sudbury in Canada, very interesting place. In Russia, for example, the North deposit. In China, in the WA chromatites are the ones in Australia and other places as well. So they are fairly abundant. They are very good sources of nickel. These are the sulfides, and the same is true for the laterites as well. But there are some differences in mineralogy between the sulfides and the laterites. So the sulfides, typically in terms of mineralogy, the main mineral for nickel is pentlandite. So if you can see that formula there, it has got nickel and sulfur, and that's the main source for nickel, obviously. But it occurs with pyrrhotite. Very typically, when you find a nickel sulfide, like pentlandite, you would most likely get pyrrhotite with it as well. And pyrite can be the common gang. Okay, so primary mineralogy for nickel sulfide is pentlandite. And also because of the way they form, they tend to have in some places very fine dissemination of nickel sulfide in the ore, okay, which means liberation is very challenging. Okay, in some parts in Australia, for example, we have very large deposits of nickel, but because of the fine dissemination of the nickel, processing is very challenging. And again, some nickel deposits may contain precious metals, especially palladium and platinum in them. You can find cobalt and gold as byproducts as well. So if you have a nickel sulfide, typically what we do is first concentrate the nickel sulfide with, say, flotation, because pentlandite is very easy to float, it's easy to control the flotation process. So the first thing I would do is, create a stream or a concentrate of sulfide, in this case mainly pentlandite, and then smelt for the nickel to be able to recover or extract the nickel out. Okay, so what are the common issues that we encounter in nickel sulfide ores? As I say, typically, if you find pentlandite, you will find pyrrhotite with it as well. So why do we care then? Because the pentlandite floats together with the pyrrhotite. So it's difficult to separate the pyrrhotite from the pentlandite. And therefore, when you have a lot of pyrrhotite, it will dilute the quality of the concentrate. So you tend to get a lower nickel grade in the concentrate. So that can be a problem. Okay, when now you sell the concentrate or you try to smelt the concentrate, it actually becomes a problem. Another challenge could be the supergene enrichment. Again, we talked about secondary sulfides forming in copper sulfides earlier. So again, you have the same issue with nickels. So in this case, although pentlandite is the primary one, you could have other sulfides like millerite, fluorite, and so on, which are again nickel sulfides, which are valuable, but the problem is they have different properties compared to pentlandite. So you can't process them the same way as that of the pentlandite. And therefore that becomes a bit of a challenge. Sometimes you have magnesium oxide content, especially if you have clays like serpentine and so on. They dilute the quality of the concentrate. And smelters don't like magnesium oxide concentration. If it's too high, then it becomes a bit challenging for smelting. So again, that becomes an issue when you process nickel sulfides. And some contain arsenic because of arsenopyrite in them. And I told you earlier that arsenic is deleterious, it's toxic. So yes, you're going to extract the nickel, but you also have to come back and try to capture the arsenic properly and dispose it because it's toxic. Okay, for laterites, again, the main difference between the sulfides and the laterites is the sulfides are nickel sulfide ores. So in this case, you have nickel bonded with sulfur, and it produces a nickel sulfide such as pentlandite, which is first easily recoverable from the rest of the silicate material. But in laterites, the nickel itself is locked within the silicate material. So in this case, you have nickel silicate materials. So you can't actually do any upgrading. In comparison, for the sulfides, we can use concentration methods or beneficiation methods, such as flotation, as I mentioned. But for the laterites, we can't. Why? Because the nickel is uniformly distributed within the ore. There's no opportunity to upgrade the ore. All you have to do is mine everything and put everything through a leach process with no opportunity to get rid of the waste material first. So what's the problem then? So the problem is obviously because you're processing the whole material, you're going to have a very high expense for chemicals and for processing. And that's one of the issues associated with nickel laterites. Okay, so typically processed using pressure leaching. Okay, so pressure acid leaching. And in cases you have cobalt as a byproduct, separating that could be a challenge. And as I said earlier, for laterites, we can't really upgrade them. So whole of ore treatment is necessary. And again, sometimes depending on the deposit type, you could have different zonation. So some are rich in iron, some are rich in nickel, and therefore you might need to account for those variations within the ore body to be able to handle different zones in the ore body in terms of processing, that is. Okay, so this is my last slide. So what are other type of deposits? I think probably the ones that are of interest, especially from the Ethiopian perspective, is maybe the Kantcha pegmatite deposit. I'm sure you guys have heard about it. I think apart from gold, maybe tantalum is the second main commodity produced. So I'm sure you'll probably hear about it at some stage if you haven't already. But yeah, so in Kantcha pegmatite deposits, the main commodity is tantalite. And I think a few years ago, they were producing tantalum as titanium pentoxide. And that tantalum pentoxide maybe is concentrated to up to 70%. And typically for that, they use crushing and then gravity separation, where the heavy part essentially contains the tantalum and niobium, and then follow that up with magnetic separation. And the magnetic part usually contains magnetite, so it's waste. The non-magnetic part is the concentrate, and that is what typically is sold as a tantalum concentrate containing 70% of titanium pentoxide, sorry, tantalum pentoxide. So are there any other byproducts? Yes, there are. Actually worked on a project on this deposit with people from Jimma and Addis Ababa University. I think one of the guys is Alberto, who is teaching you one of the topics, and also Abu Bakr. But what we found is that there's a lot of other byproducts like niobium and lithium and so on in that same deposit. So although I think they're essentially now mainly focusing on the tantalum, there's a lot of potential to recover the lithium, because if you look at that picture there, the spodumene is actually very clear, very observable, and spodumene typically contains lithium. So it's a lithium aluminosilicate. And obviously nowadays, lithium is one of the hot commodities for manufacturing batteries and so on. So it's very desirable. Okay, so there's a potential to recover lithium from that same deposit. And also there's a lot of niobium in it as well. Okay, again, as much as tantalum, there's a lot of niobium. So again, that could be a potential byproduct. So if you use a proper processing method, there is no reason why you can't recover all of them. You should be able to recover all of them. But I think the process they use now is very simple. And maybe that's why it's just designed towards recovering the tantalum concentrate only. But there should be possibilities to recover the lithium and the niobium as well. And we have similar deposits here in Australia as well. So sometimes when the lithium is not doing well, when the lithium wasn't really required, say 25 years ago, they were mainly also recovering tantalum. But nowadays, because they know lithium has a lot of value, they actually go back and they're recovering the lithium as the main commodity. Okay, so depending on the timing of, the processing, sometimes one is more valuable than the other one. So as long as you put the proper processing method to it, you should be able to recover those commodities effectively as well. So what are the challenges in this type of deposits? From our studies, we found that there's a lot of thorium and uranium in the deposit. Okay, so there's obviously issues of radioactivity with it. So you have to deal with removing the thorium and uranium from the concentrate before you ship it. So in this case, if the thorium and uranium is below a certain level, it's acceptable. If it's higher than expected, then you have to pay for that, or you essentially get a lower value for your product as well. And obviously radioactivity is one of the main issues that we can encounter in transporting material from one place to another one. So again, there are ways to remove that. I think we published a couple of papers on how you can remove the thorium or the uranium. So you can apply that during processing as well to deal with issues like radioactivity and so on. Okay. Okay, so I know maybe I talked about a lot of topics. I don't know if I confused you a lot, or maybe I gave you some ideas. I don't know what happened, but maybe you can go back and review some of these slides. And hopefully, as we go along into the actual processing of the minerals, you can refer this back again and see why we're doing things a certain way. Okay. So when I talk about gravity separation, for example, in the coming weeks, and maybe I'm talking about a gold deposit and gravity separation, you know, we're doing that mainly because the deposit is free milling, easier to process. Okay, so that's the main reason we're doing that. Or if, for example, I'm teaching you flotation and I'm talking about separating, for example, pyrite from chalcopyrite or chalcopyrite from sphalerite and so on, we're worrying about all that because we know some of those deposits actually have all of those. Okay, so we're not just creating some artificial processing method for a deposit that doesn't exist. We're actually talking about those type of processing because we know some deposits occur in that manner, and therefore our processing has to account for those variations in mineralogy. Okay, so that's why I think it's good to discuss this, but feel free to ask questions. Okay, so the more you ask, at least I know what things I need to repeat or what I need to emphasize and something like that. Okay, so let me know if you have questions. Or I think I'm also hoping maybe some of these topics are already covered in your process mineralogy, although not necessarily exact same ones, but maybe something related has been discussed. So maybe you can just look through these slides in conjunction with those topics as well. Okay, Elias, you raised your hand.
Yes.
Yep.
My question is on iron deposits. As you know, there is a Bickel iron or deposit right in Wolaga, Western Wolaga.
What deposit was that? Sorry.
Bickel iron.
Okay. Yep.
There is magnetite ilmenite deposit and the iron ore bearing hornblende, sulfide, and apatite. But our process mineralogy instructor told us the apatite makes it complex for processing, and up to now the government wants us to process it, but since the apatite makes it
I don't know what happened, Elias, but you're disconnected. Are you still talking? Okay, everyone is stuck somehow. I don't know what happened. Can you guys hear me?
Sure, we can hear you, Doctor.
Okay, yep. I can't hear Elias. I think he was asking me about apatite, but then something happened. I couldn't hear him much after that.
I think that his question is, what is the impact of this apatite in the processing
in the processing.
this reserve? I think, I think of his question is like that. I think maybe.
Okay, yep. And then they're all disconnected again. So. Okay. Yeah, I think obviously I have to look at the mineralogy first. Hopefully this is recorded so you guys can maybe go back and listen to some of that. But if they don't connect in time, I'll just answer it so that everyone can hear it back at a later stage. So I think usually when we have apatite in a deposit, and apatite is actually also very desirable because we can use it for fertilizers and so on. The easiest thing you can do is maybe look into what we call pre-flotation, because we know apatite is easy to float. We can remove apatite first before we deal with other minerals in the ore body. So I would say, for example, without even knowing too much about what's going on, I would probably suggest we have to do some sort of pre-flotation where we can remove the apatite first and produce a concentrate of apatite, and that's an additional commodity that you can probably sell and add value into the plant. Okay, but I would say that will be one of the typical things we could do. Hello, Mahatabi?
Hello?
Any questions?
No question, no question.
Okay, yep. Okay, any other question, guys?
I think most of the guys are disconnected.
Yep.
If
That's all.
if we have a question, maybe we should raise it in the next session.
Yep, no problem.
Once we see the record, maybe. Yeah.
Yep. So I will try to send you this one as soon as it. I think I have to send you the last week's one as well.
Sure.
So I'll send you those recordings. Okay, no problem. Thank you very much for joining, guys. Have a good one.
Yeah. Thank you, doctor.
Okay.
Yeah.
Bye.
Have a good day. Bye.